Hi, and welcome to the 11th tutorial video. This video will discuss two problems which involve collisions and angular momentum. The first problem states, the plank has a weight W, center of gravity at G, and it rests on the two sawhorses at A and B. If the end D is raised distance C above the top of the sawhorses and is released from rest, determine how high end C will rise from the top of the sawhorses after the plank falls so that it rotates clockwise about A, strikes and pivots on the sawhorses at B, and rotates clockwise off the sawhorse at A. This problem has three important points in time. There is the initial state, where the beam pivots at point A, and point D is lifted by a height of C. I'm going to label two similar triangles in green and red respectively, which we will use for analysis later. I'll call this time T0. Next, the beam falls to collide with the second post at point B. I'll call this time T1. Finally, the beam pivots on point B and point C is lifted. We need to find the maximum height of point C, which occurs at time T2. Before doing anything else, I'll write out the equation for the moment of inertia. The moment of inertia of this beam about the center point G is given by 1/12 mass times length squared. If we want to find the moment of inertia about some other point, say for point B, we can use the parallel axis theorem. The parallel axis theorem allows you to calculate the moment of inertia of an object about some point other than the center of mass, as long as you know the moment of inertia about the center of mass and the distance between the two pivot points. In this equation, d is the distance between the two pivot points. Since the rod is symmetric, the moment of inertia about point B is equal to the moment of inertia about point A. Furthermore, we're going to be using the law of conservation of energy, so I'll write that equation here for reference. Now let's look at the time period from T0 to T1. We can use conservation of energy to find the rate of rotation just before the collision. Using the similar triangles that I drew, we can find the height change of point G. The energy equation should be familiar from previous tutorials, so I'll skip a detailed explanation to find the rotation rate just before the collision, which I will call omega-1. Next, let's discuss what happens during the collision. With collisions, energy isn't always conserved, but momentum is definitely conserved. In this case, the forces of collision occur at point B. Since the collision forces pass through B, they don't exert any moments about B, and therefore won't change the angular momentum as measured from B. In other words, the angular momentum of the beam measured from B is not affected by the collision. The angular momentum measured from B before the collision has two components. The first component is the momentum from the rotation of the body, which is given by the product of the rotation rate and the moment of inertia at the center of mass. I'll give it a negative sign, since I'm assuming that counterclockwise is positive. The second component is the angular momentum that arises from the linear motion of the center of mass. After the collision, the beam is pivoting about B, so the angular momentum can simply be written as the moment of inertia relative to B times the rotation rate after the collision, which I will call omega-2. This angular momentum is again negative since the beam is rotating clockwise. The linear velocity of point G just before the collision is given by omega-1 times B, and the angular momentum arising from the velocity of the center of mass is the mass times the velocity times the length of the moment arm. I'll make those substitutions to the second term on the left side, which again is the angular momentum relative to point B that arises from the translation of the beam. It has a positive sign since it tends counterclockwise relative to point B. From the conservation of momentum, we can find omega-2, which, again, is the angular velocity of the beam just after the collision. Finally, we can consider the time period from T1 to T2. This is again a straightforward use of the conservation of energy equation. We can find theta and use theta to find the maximum height of C. The second problem states, the solid ball of mass m is dropped with a velocity v1 onto the edge of the rough step. If it rebounds horizontally off the step with a velocity v2, determine the angle theta at which contact occurs. Assume no slipping when the ball strikes the step. The coefficient of restitution is E. To give you a visualization of this problem, I've animated the ball falling and striking the corner and bouncing off horizontally. The key with this problem is to break down each velocity vector along the component's normal and tangent to the contact point. I'll do that for the initial velocity v1 and the final velocity v2. Furthermore, the impact of the corner causes the ball to spin, and we're told that there is no slip. Let's label the rotation rate of the ball as omega. Starting with the no slip condition, we can build up a system of equations to solve this problem. The component of v2 that is tangential to the contact point has to equal omega times r in order for the ball to be in the no slip condition. Writing that out gives us equation number 1. Next, we can calculate the conservation of angular momentum about the impact point. Just like for the previous problem, the left side of this equation is the angular momentum that arises from the linear speed v1 before the collision. We can do the same for v2 on the right side of the equation, and add on another term for the angular momentum that arises from the rotation of the body. For a solid sphere, the moment of inertia about the center point is given by 2/5 times mass times radius squared. This gives us equation 2. Finally, we have the coefficient of restitution. The coefficient of restitution tells you the ratio of relative speeds of colliding objects before and after the collision. It always applies only to the component of velocity normal to the contact point. The component of v1 normal to the contact point is v1 times cos theta, and the component of v2 normal to the contact point is v2 times cos of pi over 2 minus theta. The initial velocity component is multiplied by the coefficient of restitution to give equation 3. Solving this system of equations allows us to find an expression for theta. So that's it for today's video. As always, you can contact me at this email address if you have any comments or questions. Thanks for watching, and I'll see you in the next video.